One. We've had a wonderful technical afternoon with some great talks, and something very exciting now. I'm going to invite Lari Cujko onto the stage, who is the Startup Programme Lead at ESRIC, and I think Lari has some very exciting news. Where is Lari? I can't see him. Ah, here he is.
So hi everyone, happy to be here with you, introducing the Startup Support Program like every year. Hope that you know it by heart right now, but we still have some very interesting news to share with all of you. So the topic of today, I will try to make it too long because it's starting being end of the day. So just give you a brief overview of the Startup Support Program, the status of the commercialization part, give you an overview of the operation cluster we are currently running in Luxembourg, the selected winner of the SSP3, so the one that has been, the project will be incubated here in Luxembourg, the selected cohort for the first phase, the cohort number 4, and of course giving you an overview for the upcoming call for application that will be very matching with all that we started to discuss this morning. So as Catherine has mentioned, we are part of LIST. We are the Space Resources Department of LIST. And I will just give you an overview of what we are doing in the commercialization part of ESRIC. We are doing research, community activities, and of course we have commercialization activities. Within the commercialization activities, we are running different activities. We run hackathon, incubation. My colleague will talk on Wednesday about the acceleration program we are currently running, the BSGN. And what we are, that's true, we are the first worldwide incubation program. Like the acceleration program, we are unique in a lot of aspects, and that's very great, in fact, for us. It's not only for, what's very important to know is that we are an incubation program for early stage startups, or ventures to be preferred. So we are closing to a TRL of 1, 2, 3. And of course, the objective of the program is to consolidate the market, all the players which are currently active in the space resources field. So our value proposition is simple. We want to provide technical support, equipment, testing, of course, funding opportunities. I think for a lot of entrepreneurs, this is something that we are all starting to listen more. And of course, the ecosystem. I think that a project cannot be successful if you don't have a good project. Project will bring money. Money will not necessarily bring a good project, so that's very important. So regarding the Startup Support Program, it's also important to share with you how it works. So twice a year, we have a call for application which is open. I receive a lot of emails from all around the world. So every year, we are opening, so stay tuned, follow our website, we are opening call for application. You apply, and there are 3 phases, and each phase is building on each other. Of course, it's for early stage in the focus, the focus needs to be space resources. You need to have a kind of terrestrial application on an existing market and a project related to ISRU. So the 3 phases, we have phase 1, which is a pre-incubation phase. During 3 months, we validate the concept. We de-risk the business more or less. We heard a lot in the morning session, de-risking the business. We are supporting the different projects in that. So we de-risk during 3 months for each project that we select 5 of them. They stay in remote, you don't need to be in Luxembourg. And then during those 3 months, we help you assess the case, developing an overview of a business case. Then only 1 will be selected to get the full support of the ESRIC, ESA, LSA, and LIST capabilities through a funding support. So the incubation has to be in Luxembourg to develop a prototype or an MVP or proof of concept. And then after that period, you can stay in Luxembourg for mainly developing a 3rd phase, which consists mainly on business development. Again, as a reminder, it's not an R&D project or an incubation project, it's really dedicated to commercialization. So you need to have already a kind of prototype, a good idea of what you will do. So who is our target? That's very important. So you can have terrestrial activities, space activities, cislunar in the near future, and of course, lunar ISRU, I would say, focused in the more long term. So that's really for deep tech or space tech players. They want to develop or push their activities toward the moon activities. So how do we work as a cluster? It's important to share with you what we are currently doing as an operation cluster currently. We have a lot of projects which have been incubated through 3 programs already, SSP1, SSP2, that's how we call it, Startup Support Program 1, Startup Support Program 2, 3, 4. And through a market consolidation, we really bridge the science, the technology part, with the business part. That's very important. That's where our partner, the Technoports, plays a role. They are our incubator in that activity, in that business. And then, of course, for commercial development, we really help the companies to settle an activity here in Luxembourg and to develop a real market segment. For an overview of the value chain, here you can see where more or less our applicants are. Just to give an overview of what are the activities where they apply. We see prospecting, energy, and other activities, sometimes not directly linked to a specific field. To share a little bit with you what they are doing right now. Anisoprint, they were doing 3D printing. Currently, they have extended their activities in China. They were the first from the first cohort. Orbit Recycling, our friend Frank, somewhere here or not, they are continuing developing their recycling aspect. They follow currently what they are doing with ESA. They're developing recycling activities. They have a test lab in Rostock in Germany where they test different type of projects. Astroports, they will present during the upcoming 2 days what they're currently doing. Very successful project, doing landing pads. They haven't been selected in the first startup, but they're present here, and they develop the ecosystem, and they participate in the ecosystem here in Luxembourg. So we are proud to have all of those part of the first part. From the SSP2, for those who know, the Americans one, Above Space, they just launched something. Currently, they have been also from the SSP2. They launched on ESS to do some tests. Congrats. Luna Outpost, you all know them. They're continuing, expanding their activities here in Luxembourg. They have been part. They are really developing and are currently collaborating with ESRIC on different other research aspects. Aurora Connect from Poland. They will also have a mission soon with UAE, testing their project. They had connectors, dust-proof connectors. And of course, just to share who has been selected from SSP1 and SSP2, that's very important. We had 4 Point Space from Poland, currently here in Luxembourg. We have Litigo Space from Czech Republic. You can visit them. The startup is present there. So they're very successful. They're using in situ LIBS technologies to test materials. And of course, an important element to share with all of you is who has been selected for the SSP3. And we are proud today to announce officially that the one has been selected. It's Space Backend. It's Dimitri Goldenberg. Where are you, Dim? Dimitri, maybe it's good to share, to say a word. For information, Space Backend passed the 3 months, the first phase. And they have been selected with the jury members from MISA, LSA, LIST to be part of the next cohorts. And it's important to share presence here. Just a word, maybe.
Thank you very much for the support received from ESRIC. I am very proud to be part of the incubation program. I should say that last year I have first time visited this conference because I had some idea in the mind, and I spoke with companies to make a validation of the idea. I came back to home very inspired. I have established a company, and then we have been accepted to the ESRIC Start-up Support Programme. We have received a lot of assistance to identify the real scale of the company, the real potential scale of the proposed solution, and to identify the right strategy, business strategy, go-to-market strategy, for lunar applications and for rest of the applications. Thank you very much for the support.
Thank you. Big applause for them. Yeah. All we can give them. Small pictures is always important.
Okay. What?
to represent ESRIC.
Thank you.
Thank you. Good pictures to share on LinkedIn. It's very important to stay connected. It's true. So regarding the linear version of the space resources value chain, I think that we can discuss if it has to be presented like this or not, but I think it's a simple way to formalize where the different startups are on the space resources value chain. And we see that through the incubated project, we have a lot of them on different aspects. A lot of them are on the robotics field, prospecting technologies, energy, and that brings us a lot of information regarding how we should drive our next calls for application, where the startups could match, where are the future missions which are planned by space agencies, by private players. That's very important. That gives us a valuable information to how to select and how to scout them. So if you remember, from the first cohort, 4 Point has been selected, but again, all the different projects are still very active. Even if not selected and funded by ESRIC, they remain extremely active and they work together. I think this is the biggest success for us. They continue collaborating. Sometimes we discover they want something, they develop something, we're not even informed. From the SSP2, it was slightly ago, but still there are a lot of discussion between the different other ones with sometimes tremendous results as being present on different missions in UAE, for example, for Aurora Connect, for Luna Outpost. I don't have to mention anything about that, you all know them, but it's very active. From the third cohort, of course, it was Space Backend, Dimitri that you just met that has been selected, but still all the different players continue to remain very active. Orbital Mining Corporation, they are present here. They are very active with the DC converters, so do not hesitate to talk to them. Solstice Mining with the Regolith simulant, they are present here. And what I want to announce as well is the new cohort. All those startups are more or less present here. It's a lot of information regarding the startups, but it's good to know that you hear that they are present, they are here. They're just sitting there, so go to see them, discuss with them, create this business relationship. It's important. We are discussing from the beginning ecosystem, economic ecosystem. They are here. Now it's the moment to discuss with them and create synergies. You are maybe the future customers. We often discuss about customers. Go to see them, purchase their products, start collaborating with them. So for the first one, we have Niamin from France. They have a project for oxygen extraction. The second project is from Germany, Neurospace. I think that some of you already know. And even if they had just started to be selected, they already discuss with some of the partners from some of the startups which have been pre-selected, like Orbit Recycling. Space Engineer, project from Portugal. They have material composites, for some of you who knows. They have smart materials. And of course, Tumi Robotics from US. I think Francisco is present here. For the terrestrial applications, go to discuss with them. So here they are. If you meet some of them, I hope I've chosen the best pictures. Don't judge me on that. So they all benefit from the same approach. I'm just sharing here some aspects of what they will get of that. Technical support, business support, IP support, legal support, and of course I put the funding, 200,000 they can receive at the end of the pre-incubation phase. One will get the funding of 200,000. I put it at the end because I don't think it's the most important. It's really the project you are driving, the collaboration you can get, which is the most important. Of course it's important. We work closely with ESA, Commercialization Gateway, and all of them. This is we are part of the big Business Incubation Center network. We collaborate with them to have technical expertise. That's very important for every single startup. And what I wanted to share also with you, it's our roadmap. As I said, all the information we collect from the application, from the scouting approach, it gives us an overview of the roadmap we want to have, but also from the research point of view, what we want to achieve. And you see here, that can evolve, of course, but the next one, the next goal we are targeting, it's really exploration and prospecting technologies. We talked about, from the beginning, I think the first discussion was exploration. prospecting technologies. And I think that will be the biggest challenge for everyone. No, we will make it happen for everyone. So let's see how the market, the ecosystem will react to that.
A new era of space exploration is here.
The first worldwide incubation program entirely dedicated to space resources.
Who's the customer? What is the business plan?
Access with facilities, offer technical support directly from European space agencies. We're part of this vibrant ecosystem and an international network of partners.
I think that's where the SSP comes in.
Space resources starts now.
Find out how you can be part of the story.
So again, this is the next call that will open in May, focusing entirely, it's a thematic call, on exploration and prospecting. As I said, we have been talking from the beginning. We have heard a lot of things from ESA, from JAXA, exploration. So now let's make things happen. We are launching this call for application. There will be startups applying to that. We are looking for experts, VCs, investors. This is the right moment. And of course, the program is open for all countries around the world. So everyone is eligible to apply, at least for the first phase of the program. So we are reaching everyone, every single country. And as I said, stay tuned. We will open the call for application in May. That's an opportunity for everyone. And again, nothing will be possible with our researchers, which are present with us, our partners, stakeholders, and of course, the startups, the ecosystem, the cluster that we are currently building here in Luxembourg, all of them make the things happen as well. The collaboration, the consolidation starts here, in fact. And if you have additional questions, you can reach our director, Catherine, or myself. Thank you very much.
Thank you very much, Larry, and I know you... No questions that I can see. I can hear a little bit of a fuzz of noise outside. I think I'm very grateful you're still in the room. 2 more talks to go, and then we'll all be going out there to make a bit more noise and to look at the posters as well. But first of all, please welcome back to the stage Robert Lindner from ESA, who is going to talk about development of miniaturized volatile analysis techniques under the ESA... No? Okay, he's got something to show us, I think, under the ESA technology development element. Are you going to show us something? Excellent.
Thank you very much. And yeah, sorry, it's me again. I would like to talk a little bit about, let's say, things we are doing in ESA with respect to volatile analysis, eventually, let's say, evolution of instruments which are out there under the technology development element. So I'm going to talk a little bit about the background, the motivation. Then I'm going to tell you something about the TDE program as such, because it might be interesting as well for others. About mass spectrometry, gas chromatography, sample sealing activities, and then give a conclusion. So the background and the motivation. In principle, volatile analysis is really needed for ground truth data. And we heard it in talks before. That's really essential and important to map and to see what we have. To measure is to know. And in this respect, there's already in Europe, and obviously there are, of course, even much more in the US and some other countries, quite an extensive flight heritage in terms of flying mass spectrometers and as well GCMS systems. You can see, for instance, on the right top side, example of the Ptolemy ion trap mass spectrometer. And just to give you an idea about the size, so this is not my lunchbox, but just in order not to destroy this 3D printed model, this is more or less the size of a mass spectrometer as we have it right now. Yeah? So it's already pretty compact. It's pretty, let's say, optimized in terms of mass. And of course, as well, trying to find a sweet spot between mass, engineering budget, and as well the performance of it. We have further flights foreseen for that. Another example, for instance, on the bottom right is the GCMS system of MoMA, which is already quite elaborate, quite compact. We have several GC columns which are implemented there, together with a laser desorption ion trap mass spectrometer and the laser. So it's quite a heavy beast of about 16 kilograms, but it is very versatile, it is very performant in this respect. Now the question is, of course, can we use, let's say, the budget constraints, engineering budget constraints, to make things even smaller, or actually ensure that we eventually can fit instruments with a smaller size on maybe cheaper mission, lighter missions, smaller missions in this respect for surface measurements. And another issue is, of course, the cost. Unfortunately, not taking into account the launch costs, which is a different story, we're still talking about something like 1 mega million and even more in terms of euros we need for the development and build of such an instrument. Yeah. So we are looking for ways to provide smaller and lighter payloads with eventual, obviously, some lower performance, because physics simply gives you some limitations in terms of dimensions for mass spectrometry, and eventually give you as well a perspective of implementing redundancy, of maybe having several mass filters on board, or let's say you have a distributed type of focused science where you can have several instruments deployed and dispatched. And you can consider as well, since we are at an ISRU conference, to use this kind of tools for process control. Yeah? So can we make things smaller with an acceptable loss of performance? And the idea was, of course, to investigate whether MEMS technology can help us with that. So now I'm going to have a little advert break here to show you about the TDE program, which has been funding these activities. This is a part of the ESA mandatory basic activities. So this is essentially ESA, if you look at ESA, like being a country club. So if you want to join the country club, you pay your subscription fee, and this is essentially paid out of that. If you want to do other things like optional programs, like if you want to play golf in your country club, you have to pay extra. So every ESA member is paying for this program. So every ESA member has as well access to this program. Very important. So the first step is that we, for this program, this is part of the way we are implementing our technology strategy, yeah, which is being defined. For instance, in the frame of the European Space Technology Harmonization Roadmaps. So this is an exercise we go through ESA internally, but as well together with our stakeholders and industry to define what are our technology priorities in some areas. And it covers essentially all ESA programs and technology disciplines, yeah? Be it software, electronics, EEE parts, robotics, exploration, and one of them where this activity was funded on is really looking at the instrumentation-related aspects. In this pie chart, you can see more or less a distribution. Okay, this is maybe another version of the Jerry Sanders eye test, so I apologize for that, where, you know, what are the different disciplines which are drawing on this program. It's based on a 2-year work plan and with yearly updates, so we're always updating it. And essentially what you can see, for instance, on the top right is the area of TRL. And this program is really based, or let's say focusing on low TRL, TRL 1 to 4, say 4 plus. I mean, if you close both eyes, maybe as well TRL 5-ish. And most of the times we start at a TRL 2 and we achieve a TRL 4 in this area, in this realm. Coming back to what we did now in the past, so we had an activity, or we still have an activity with the University of Wrocław in Poland and Cryotech to study the possibilities to build a MEMS-based mass spectrometer. The mass filter itself is based on a quadrupole, so for those familiar with it, they know where to put it. And we assessed 2 concepts. One of the concepts was to build really full MEMS-based mass spectrometers, so the electrodes The ion optics, the pressure sensors, and the detector were all based on silicon and glass type of MEMS technology. And then we had as well the exploration of a hybrid approach where the electrodes itself of a quadrupole was based on, say, precision machining somehow, and the rest was based on MEMS. The goal was really to do functional and essentially as well performance tests for test gases or volatiles up to 150 AMUs. And you can see, for instance, here in the bottom left, the two samples of the mass spectrometers on a test table as we have designed them. And here, of course, before we did that, we did an extensive modeling with the University of Wrocław to see how the field and the potential would look like according as a function of the geometry of the MEMS-based system. Again, that's not too much to look at for you from let's say, far away, but essentially what we achieved was we did tests, we built this thing, we manufactured it, we tested it, it works, and then we subjected it to, let's say, environmental tests. We took CubeSat specifications for the environmental tests as a baseline to, have some sort of a requirements to shoot at, because, some sort of a CubeSat, let's say, envelope for mission was something we had in mind in the beginning. So we did shock tests, vibe tests, TVAC tests on the whole setup, on the two different, let's say, full MEMS and hybrid MEMS setups. We learned quite a lot during the course, but we could essentially prove that the full MEMS setup, let's say, almost met all the specifications, even post-test. The hybrid one of the hybrid versions met them all, and the other one was failing on one specific ones. So we did measurements with test gases. In this case here, you can see some results up to 50 AMU. So everything which is really light, really volatile, can be detected with such an instrument. Now then the next activity we were following in was to really look into whether we can build a gas chromatograph on a MEMS technology. We have gas chromatographs on SAM, on MoMA, on GAP, on Rosetta, which are bound to fly or already or flew, essentially, and worked fine. And here the idea was really to implement the MEMS columns, so the separation stage in the MEMS technology. And that gives you, of course, then the possibility and opportunity to add several columns if the resources you're using are pretty small. Just for indication, these chips, these are the column chips you can see here. They have, let's say, dimensions of about 5 by 5 centimeters. So that's one thing. But the GC column itself, for the separation of your volatiles, is quite often not enough. You obviously need a detector, and you need as well a concentrator. And that's what we've been focusing on as well. So this is ongoing. We are still need to test it at the moment. We are still in the integration phase with some specific challenges we need to resolve. And last but not least, so I'm almost running out of time, I wanted to mention an activity which seemed to be not very exciting, but in the end of the day, it provided very valuable data. The problem was that in order to do volatile analysis, you need to have a containment of your sample. You need to heat up the samples to elute your volatiles. This is often done in ovens, and I think Philip in the previous session even showed these ovens, where you heat up the sample up to 1,000 degrees. Challenge is you need to seal them. So you have a gasket, and in this case a knife edge, you press into this gasket, and you hope it's working. The specific challenge is that you need to start the sealing at extremely low temperatures, because you do not want to lose your volatiles in a lunar environment. So you start to seal at, say, minus 100 degrees, and then you heat up, and then this seal itself sees temperatures up to 300 degrees. So to find a sealing material which is really elastic, or let's say plastic enough, over the whole temperature range in order to provide you a good sealing was already a challenge. We tested several ones. The best one was PTFE. And we did tedious tests on different, let's say, dust loads under different temperatures to measure the leak rate. And that was quite very educative and very important as well for the design of the Prosper ovens. And you can see, for instance, here, CT micrograph in order to understand as well how these dust particles are being indented. For your information, we tested up to a dust load of about 10% obscuration factor. And this is, of course, something we say, yeah, I mean, why didn't you test it to 100%? There, of course, things get critical. But this is a realistic dust load you can expect, say, in an instrument where you drag in any kind of dust contamination. So that was very, very informative and very useful as well. So to conclude, the viability of MEMS by mass spectrometry is proven. We are working on the optimization and increase of the robustness. So next step is to increase, as I said, the robustness and to do benchmarking tests against performance of current space-worthy designs to see how do they fare with that. That's the potential to reduce eventually cost and engineering budgets within acceptable performance limitations. Things like electronics will most likely look very similar. So there the limitations are limited. And then new MEMS GC concept is now designed, and we are working on that. We have several other studies as well working, for instance, on sealing technologies for ISRU processes where we really are in a high dusty environment and very high temperatures. And this is now just being finalized at the moment. We have as well studies performed on dust mitigation techniques. For instance, how can you get rid from dust from surfaces with active means? And these are all things which are ongoing under this program. So with this, I stop and thank you for your attention.
Thank you very much. He raced off before I asked him any questions, but that's okay. I wasn't going to anyway. I know that we're one talk before the evening. And this is Karl. Welcome back, Karl, to the stage. It's Karl Hibbitts. Thank you.
Hi. Thanks, guys. It seems to be my honor to be the last talk in the session, standing between you and your break or dinner. In this case, I promise to make this one a little bit slower so everybody can understand, but not any longer. We're going to start with an intro analogy I came up with, but I really like the last speaker's mention that to measure is to know. And that is pretty much the theme of what I'm going to be talking about today, which is understanding water ice at the poles to enable prospecting. All right, so, all right, great. I'll look down here. I'm going to go over this somewhat quickly here because this is simply rationale for why we want to do the ISRU prospecting for water ice. It's really the last point that we need to keep in mind. We cannot say enough. Inclusion of countries and communities who cannot by themselves undertake space exploration is something that isn't really a technology driver, but it certainly is something that we want to keep in mind and try to do. For this talk, I'm going to keep the bottom line up front with a little introduction that the understanding the nature of the water ice on the surface of the moon will enable us to understand not only where to look, but also how to look, what technologies are needed for the extraction of it. This lack of knowledge is really the one biggest gap we have, I would argue, in water ice ISRU. So the purpose of this talk is to identify where technology development is needed and where it's not needed to enable operation of the PSR, not just for prospecting, but also for extraction and processing for operations of the PSR. What I'm about to present is a multi-step process, an idea, a one concept for an international prospecting campaign for water ice on the moon. It's not the answer. There can be several variations. The point of this one is to explore explicitly options that we may want to take to identify these technology gaps that exist. Okay, so we start with confirmation, determine which PSRs actually do contain accessible amounts of water ice reserves. And then goes with refinement, which we often talk about using rovers or some other ground truthing process to precisely locate these reserves. And finally, ending up with a detailed assessment, characterization of the selected reserves. Interestingly, I might jump to the very end, even though we're here I'll talk about need to know in just a second. Many of these technologies for measurements, to know, already exist. That was part of my driver here, is to try to come up with a concept for a international or any kind of campaign that does not rely any more than necessary on the development of new technologies so that we can execute this as quickly as possible. But let's start with what we need to know about the water ice reserves. Location and abundance, probably to about that of the lander or the ISRU processing facility that you will want to deploy down there. That means to tens of meters. And with current technology, we can extract an upper meter or so to a wide or to a depth of the upper meter or so is needed. At a percent, really only about 1%, because economic viability for water ice, other studies have shown, is about a 2% level, right? So we don't need to know down to 10 ppm. We need to know better than 10%. So, 1% accuracy is fine. At an abundance to support anywhere from 10 to 100 metric tons of use per year. This comes from a supply and demand study that ESRIC led a few years ago, right? Over a year, so this isn't a day, so the rates really aren't that great. The physical state needs to be known, because this directly affects the technology that would be deployed in its extraction, i.e. is it granular, ice-coated grains, indurated, do we need to do beneficiation or not? And the exact extraction methodologies depend upon this. And finally, composition is very important. Yes, water ice composition, H2O, right, not OH. But more importantly is the contaminations in it, SO2, things of that nature. Other volatiles, not necessarily hypervolatiles, they'd be interesting as well because they can be additional resources to extract. But for water ice itself, we'd like to know certain contaminants that can affect the processing, SO2 being the most, most deleterious. So I want to, again, spend a few minutes. This is the extent of the eye chart that I get, right? So not too detailed, but I would argue important information, quantitative information. What we currently know about water ice is limited, but not insignificant. We know it does exist there. 2 to 8% has been discovered through the Cabeus, in the Cabeus crater through the L-Cross impactor, and it's modeled and very likely to be disseminated water ice. We don't know if it's ice-coated grains or not, but it's disseminated. And this information is called pre-2010. We also know that 100 ppm of hydrogen, which equates to a few thousand ppm of water if the hydrogen is in the physical state of water, does exist in in the polar regions. We don't know if it's in the PSRs or not because the spatial resolution of these measurements from the neutron spectrometer is on order of 40 kilometers per effective pixel. Not that neutron spectrometers work that way, but per effective pixel, about 40 kilometers. This is larger than most PSRs, and thus we really don't understand where this water, if it's water ice, is. And that leads to the first step that I mentioned earlier, needing to find the general locations of it. We do know that there is surface ice in this PSR. Now, this is a resource but not a reserve because of water ice, most likely a frost, has been discovered by instruments that only look at upper microns or 100 microns. M-Cube instrument on the Chandrayaan-1 mission is widely analyzed in great detail. UV measurements have shown water ice is also present in the LRO measurements by the UV spectrometer there. And the LOLAR instrument also has detected water ice in these PSRs. Again, all that is superficial, not a reserve, but there's water ice there. We don't understand how to relate surface frost to the subsurface frost, to any surface abundance. And possibly, to skip down to the bottom, the VIPER mission itself will make measurements to relate the understanding of subsurface to surface measurements. But to continue with surface measurements, we do have upcoming missions that are already selected and will be flying that may give us some insights. The Trailblazer mission, although it is also an imaging spectrometer, will have the capability of measuring grain size information, and one can potentially infer from grain size information if that origin of that ice you see is frost, fine grain, or if it's large grain, excavated subsurface deposits of water ice. In fact, the ShadowCam was hoping to see some evidence of that. It would have been sensitive, or is sensitive to tens of percent of water ice, because it only looks albedo, it requires about 10%. It hasn't seen that. That doesn't mean that there isn't water ice in the PSRs. It just means that the abundance in the surface deposits is less than 10%. That's not at all surprising given Cabeus, it's a few percent of the most. And there are athermal as well as athermal processes that would absorb it anyway. Radar observations are very suggestive, but we don't really know. So I just want to say that I'm keeping in spirit of this mission, of these talks today and running behind schedule, but I'll try to pick it up. The 3 tiers are, first one, orbital confirmation of ICE and PSRs. I want to take the opportunity to again mention maybe more of an interest in your being able to propose to the RFI or respond to RFI, that DARPA has released an RFI called Shell, which one of the themes is explicitly to understand a orbital mission that would be capable of making these measurements, very similar to what I'll be talking about here. Don't need to go into too much detail. Again, locating specific reserves and detailed assessment. Anything we do, it's very important to also have at least a canonical understanding of these requirements, but I want to emphasize these are my personal derivations of what would be necessary. These are not approved by NASA or vetted by any committee, but these are representative of the kind of measurements one would need to make. I want to point out that very likely, I mean, from our assessment, these instruments already exist. Look to the far right. And other missions, these are just examples. Other instruments that were presented today would work just as well, right? Perhaps even better. But again, as I just talked about, we want to understand the water abundance about 2% plus or minus halfway percent. Contaminations already talked about. Spatial scale, I'd argue we want to start with understanding it at a large scale, then moving down to the high resolution. So how do we do that? Orbital reconnaissance can do this, move from our current capability of 40 kilometers to just a few kilometers with a very low altitude mission to measure, in this case, I'm proposing neutrons, because the spatial resolution is basically equivalent to the orbital altitude. We can get down to 10 kilometers altitude, shown here through orbital analysis. In the middle plot, showing that over certain terrains, your altitude can be as low in the blue line and green lines, less than 10 kilometers. But where there's high peaks, such as in the red shown on the left image, you get much, you might hit them, so you have to be very careful. And that is actually shown in the lower right plot, showing that in that orbital trajectory, if you don't raise it up, you actually start impacting some of the high-level terrain. And what does this lead to? This leads to the fact that you need to probably have the ability to change your orbit on a daily basis. What that means, so how do you do this? Do you want to rely on comm from Earth, where that's going to be lost, and if you lose that comm or that trajectory maneuvers are not made, that you then crash in, or do you want autonomy on the spacecraft to do these? Well, I personally would recommend some autonomy on the spacecraft, but the decision is up to you. So the next step is more of a detailed assessment. I just notionally picked Shackleton, although the slopes of its impact or of its crater walls are rather steep, and that probably isn't where we'd go. I don't want to bias anybody to other areas, so let's just pick Shackleton. What this will require, if you even have 10 kilometers or even 5 kilometers effective pixel, you have 25 to 100 square kilometers that you have to explore to find a reserve that's at the scale of 100 meters. So this itself is non-trivial. It's basically impossible at 40 kilometers. You might be able to do it at 10 to 5 kilometers on the side, but still, our modeling shows that you need a rover to last 6 months to a year in there. And how do you do that? Well, it's probably not going to be nuclear, not if we want to do it near term with current IRCU. Batteries aren't good enough. The technology that's missing here is honestly power beaming from our perspective. There may be other options we don't know about, but power beaming is a technology that's being developed that may actually be able to solve that problem. Okay. Finally comes with a detailed assessment, which we would suggest to be very much a Viper-like or other ESA-like rover that has that has those current capabilities to make the measurements. The question again comes down to durability, lasting up to a year, and power. Those really tend to be the questions that you have to address. Thermal is also a challenge. We keep in mind that this is a PSR-only rover, so you don't have to design it for daytime and PSR operations. So in a way, thermal design could potentially be even simpler. Okay, and that I'll skip over this due to a lack of time, but plenty of work has been done on that. So takeaways. 3-tiered campaign is one potential feasibility approach. The point of this, though, is to delve down into what technology needs to be developed to enable this. I would argue that the technology development may be limited mostly to developing a power solution for operating PSR and enabling long-duration operations. And I'll leave it to everyone else to explore how to do this in greater detail to pose to your respective opportunities. Thank you.
Karl. Thank you. I don't have any questions, and I'm sure they'll catch you over a drink.
I wonder why. It is quite late.
And there are no questions online either. I think people are moving off towards dinner or various things like that. Thank you so much for those of you joining us online. We'll be back again at 9 a.m. tomorrow. Thank you for still being here in the room. Of course you're still here. We've had wonderful, wonderful talks all afternoon. Now it's time to look at the posters, a poster session, voting for your favorite poster. At 8 p.m. tonight, we have the Space Cafe in Clausen in Luxembourg, I believe, in a place I haven't heard of before. So I hope you enjoy that. But don't enjoy it too much, because we will start here at 9 a.m. tomorrow. And I got the information wrong before. A gentleman came up to me. His wife's phone is missing, so it hasn't yet been handed in. So if you find a phone anywhere, please do hand it in to reception. Apparently it's in a black case. Thank you very much.